Who wants to attend the discussion should sit down. And then stand up to say what they want to say. Okay, so I have a request from the organizers here. People that want to participate in the discussion and want to be heard when this is saved for eternity should come forward and speak to the microphone. But you don't have to. So, okay, so I think that we have several options with this discussion because there was already a discussion of, I guess, theoretical computer science and discrete mathematics in the Dead Sea. I'm not sure that we got all the conclusions about the future of this field in the next century, but almost all. So we can first go into detailed questions or discussions to the speakers of this morning. We can talk about the various like philosophical issues that Noga, for example, raised in his the last slide of his lecture, and we can also go to lunch early when we are done with that. So, anybody?
He didn't say it.
I have a question.
Okay.
First, I have a comment.
Important, no?
He raised this problem, the Ramsey theory, the Ramsey numbers for large yet upper and lower bounds, and he put these numbers between two exponential growth rates. It's a much older problem, which is already using the probabilistic method by Minkowski, about high-dimensional lattice packings. I mean, Minkowski considered this. He wanted to make lattices in very high dimensions where the shortest vector is very long. And we know very little about that too, but Minkowski, already using what is called his mass formula, which averaged over all lattices, discovered a lower bound, inexplicit lower bound, because it was an averaging procedure. He didn't call it a probabilistic method, but it's entirely equivalent, and his result is essentially optimal. Schmidt, the same Schmidt he mentioned, has made a very small improvement of that. So there's this bound, which is very important in number theory. It goes by the name of Hermite's constant in that case, as to how it behaves in the large n limit. So in that case, you have the exact same feature. You have these non-constructive or methods of averaging which give good lattices, and you have a lower bound that way, just the same as the Erdos thing you wrote down. And then you have people chiseling away brilliant results of getting improvements. Blichfeld was one, but there are better results.
And are explicit.
The upper bounds are upper bounds. They show that you can't pack better.
But here are also explicit constructions that are exponential. Not as good, but are
in the lattice packing?
Right, yeah.
Yeah, no, it's nowhere near these two constants. No. So the
Yeah,
behavior, if you take the limit of the log of this growth rate divided by n, we know it lies between 2, and Blichfeld gave 4 in the upper bound, and you can get slightly below 4 using linear programming methods. But so my question there, I think it's completely unclear which is the answer. I think most people would guess that the random is best, at least in this crude asymptotic fashion. So I'm curious, I would like to see the views of people who've thought about this in the, say, Ramsey case, as to what might be the right answer, or is it just not enough understood to make a guess? So one has these two constants that you wrote down, and is random best? Is random best? I like that question. Is random? Sorry. I got a question.
I just would like to mention one example where random is not best. It's not any of these, but it has something to do with discrepancy theory. So you want to find a 0-1 sequence of length n, which passes certain tests for randomness. And the test is that I pick an arithmetic progression, and I want to have about as many zeros as ones in that. And then I look at the maximum, the worst arithmetic progression. And the question is how far off I will be. And you would say that, of course, to pass randomness, you want to be as close as possible. And for for a random sequence, of course, you will be off by square root of n, just trivially. And the question is, can a sequence be non-random for the opposite reason, namely that it's too good? And Roth proved, gave a lower bound of 4th root of n. You can never be better than 4th root of n. And of course, it was thought that is just you know, it's a fluke of the method. And it should really be square root of n. But then Beck actually constructed examples where it's 4th root of n. So in some sense, it's a very strange case.
They're not random.
They are not random. So you can beat randomness in some cases.
Yeah, actually, in your lecture, you had another example of Schmidt. I mean, the result about, say, yeah, but maybe I should use just to encourage people to use the microphone here. Because, so actually, this example, am I using it? So actually, these examples that you mentioned of the discrepancy of points in the square, if you put random points in the square, the discrepancy would be square root n. But we know that these Hammersley sequences give discrepancy log n. And I think in general, so also for Ramsey numbers, and in fact for lattices also, or for the related question in coding theory, error correcting codes, well, in error correcting codes, in fact, we know that random is not best. You mentioned it yesterday, and it's I think that in all of them, probably random is not best. So usually,
So you really think in the RAM? I'm not talking about the fine structure.
sure, yeah, you're talking about the that's right.
Just the exponent.
Yeah, but again, so in the Ramsey things there are questions that are pretty similar. So for example, people consider suppose you want to two colors edges of a complete graph, and you want to minimize the number of monochromatic complete subgraphs, now of a certain size. Now this is exactly like Ramsey, because the original Ramsey is that you are trying to two colors the edges of the complete graph, and you are trying to minimize the number of monochromatic complete graphs of a big size, of size constant log n. You want to really minimize it to get it below 1, to get it 0. But how about if we just try to minimize the number of monochromatic triangles, or the number of monochromatic complete graphs of size 4, or something like that? And this, in fact, it was conjectured, the same guy who makes all conjectures in combinatorics, that random gives the truth always, and there it was disproved by Redel and by others. So if we want a coloring of the edges of a complete graph by two colors, trying to minimize the number of complete subgraphs of size 4, let's say, or anything bigger than 4, then the best is not random. There is some explicit construction. Now the same thing is true, I guess, when we have these very highly regular structures like projective graphs of incidence graphs of projective geometries, or a construction for Zarankiewicz problem where you want very dense bipartite graphs that do not contain some forbidden subgraphs. Then usually there are these random bounds, and for the general case they are the best that are known. But in all the cases where the correct behavior of the exponent, and here it's again the exponent of n, where the correct behavior of the exponent is known, this comes from explicit constructions and never from a random one. So in general, I think, I mean, of course there are examples where random...
Just think the lattice packing case, most people believe that random is best.
Well, but not for error correcting. I always thought that it's essentially the same, right? I don't know. Most people believe that Gilbert Farshamov, or you can, it's not known, right? But it could. But it's, yeah, sure, we can.
I thought it would be assuming to answer Peter that he has a counterexample to this statement. Namely, one of my, that random is best. So one of my favorite problems in graph theory is something for which the current record is from your paper with Lubotsky and Phillips. So this is for how large the girth can be in a graph. So you want to construct regular graph, deregular graph, with n vertices with no short cycles. And the best construction that's known come from these LPS graphs. This by far beats what we know how to do with the probabilistic method. So both to perhaps recall things that were said here before and to state a new thing, the reason often random is best, but certainly not always. There are situations where much more orderly constructions beat the random constructions, such as in error correcting codes, perhaps such as in girth, we don't know. But also random, that's perhaps an idea that is very important and somehow didn't appear in the talks that were given here today. Random can also be, I mean, we are modifying and really improving our understanding of this. So just to say one thing, and certainly all the combinatorialists in the audience and the computer scientists know what I'm talking about. For example, doing a random construction and correcting it, or doing things that have been developing very well in the last decade or so, what we perhaps now call the semi-random method, where you are doing a random construction not in one fell swoop, but you take a little step towards your construction, you perhaps do a selection or a little correction, then you do another random step, and so on. This is a general paradigm that is giving us lots of very interesting results in the last decade or so. And often we can do much better with such methods than with just straight randomness. So the answer is much more delicate than, you know, this is the best or not.
Yes, I was mentioning the graph. You take a graph on a random, or how you take the pool from where you take them, yeah?
No, this is an extreme problem. This is an extreme problem. I give you two parameters. D, which I usually think of as fixed, so let's say D is 3, cubic graphs. D is fixed, and n tends to infinity. So you want large graphs with no short cycles. And you want them to be, you want the bound on the first cycles to show as late as possible.
Just what Noga explained to me, well, you have a few short cycles there, you can remove them.
So that's one possibility. I mean, it would, that's one possibility. It's far from being the best, but one thing is you could take a random construction.
No, but we're talking about the constant.
The constant. So D equals 3.
Yeah, the order of magnitude there is, the order of magnitude we know, but the constants, I mean,
That's
this is,
you get constant love.
Yeah.
The issue is the constant.
Right.
What's the choice?
right.
So I'll take the microphone. So I'll just, I mean, sort of putting a twist on what Peter really meant. I mean, I don't have more examples or counter examples, but just use it as, I mean, the question of whether explicit meets random is basically the question that we are trying to understand when in complexity theory, and I don't, I mean, because we know that random functions are hard and we are searching like crazy to find one explicit function, which is difficult. We know lots of them that we think are difficult, but we are looking for one. And I talked about this more than my time allowed when I gave my talk, but I want to at least ask one question of this type that's totally different and maybe very appealing to, you know, to a mathematician of any sort that learned a couple of years in college. So think of, you know, fix whatever field you like. I mean, it's nicer to define if it's a finite field, but whatever. And think of a matrix as that you want to diagonalize. So using Gaussian elimination. So if it's an n by n matrix, let's say we count the number of row operations you do till you diagonalize it. It's always at most n squared operations. It's a triviality, right? And in fact, for random matrices or for most matrices, you would actually need this number of row operations. Now give me one matrix that you know, I mean, something that you can define, an explicit one you can easily define for every n, that will require more than linear number of Gaussian operations. So that's... Yeah. Okay. Yeah, you have one?
Actually, I probably have one, but I don't know to prove.
Yeah, I have more than one that I cannot know how to prove, but...
Yeah, but
okay.
It's a free discussion, so yes, indeed, I want to say that...
No, it's not.
Okay. Okay. So, yeah, I want to say that relating to this and also related to the Ramsey numbers is that usually we know, actually, examples only we don't know to prove. So the thing is that, indeed, random is much easier. So that's why we use usually the probabilistic method. I mean, actually, as far as we know, for Ramsey numbers, Paley graphs are probably an example. So if we take a prime p, not for every prime, I guess, but for infinitely many primes, it should be true that if we consider the graph whose vertices are the integers modulo p and 2 are adjacent if and only if their difference is a quadratic residue modulo p, p is 1 mod 4, then it seems true that these graphs provide, in fact, better bounds for Ramsey numbers than random graphs. This is true for small cases. It has been checked. And now it is true that still there are infinitely many primes for which they are not as good. So the smallest quadratic non-residue could be log p, log p infinitely many times, but it could still be true that for infinitely many primes it beats random. Now, presumably, this same Ramsey matrix considered over GF2 is a good example for diagonalizing, right?
Conjecture, wishful thinking?
No, I mean, I'm just because it's a pseudo-random matrix, right? But the thing is that usually all these things are horrendously difficult to prove. So the best bound we know for the smallest quadratic non-residue is only p to the 1 over 4e or something, I don't know, but some specific power of p.
In this discussion, we're allowed to assume all previous conjectures made in this conference. So the Riemann hypothesis sorts that one.
Okay, right. But in fact, even with the Riemann hypothesis, so the smallest quadratic non-residue is okay, but not the biggest clique, right? So even if right, so even as far as I know, even with the Riemann hypothesis or anything, right? But yes, so I think I mean, like the only point I wanted to say, so I don't know why I'm mumbling so much, is that random is often easier to get, but when we really can get a hold on the best explicit thing, then in fact by definition it is better than random, right? If it is the best. But often it is indeed significantly better. Only it's much more difficult. So usually we have to know much more, and that happens also in Avi's questions, in many de-randomization questions.
Just to defend the other viewpoint.
Why won't you take this?
Just that all progress that's made in Ramsey theory, if I'm correct, and in this lattice packing, only comes from one side. That is, the upper bounds are improved, and there's this.
No. So actually, the best known. Yes, the best.
I'm talking about in the Ramsey problem.
Well, I mean in the Ramsey.
Not T3, TT.
Right. Yeah. So in the diagonal, in the diagonal, I agree. So it still came from there was a progress by a factor of 2, but but something ridiculous.
So what I'm saying is the
I
decreasing
agree.
of the exponent is always on the other side. So I just.
No, it never changed actually. The exponent never changed. Never changed. Yeah. Here it just never changed. So everything that was known in the 40s, in the exponent definitely, but even far worse than that. The lower, far worse than the exponent.
Okay, that's interesting.
Right. So it's really.
We'll begin to cite Don. You don't object? Don, if I state your conjecture. If I state your conjecture, and so the conjecture says that Don privately told me that if you have some kind of sequence of numbers generated in some regular way, you should believe according to some criterion behave randomly, like your case. Then in most cases, this will be true and unprovable. And it's very feasible if you think about that, yeah? most of this conjecture is probably true and unprovable.
Can you agree to the true? I'm not sure.
They're true in certain sense because you just it's true, right? You correctly stated, yeah? But at least they're unprovable. For example, conjecture of this nature. If you have a quasi-random way to generate graphs, and then you conjecture they behave in a random way, like a Ramsey number, and it's quite likely the statement to be true, but unprovable. And moreover, this mathematical theorem can be proven, I believe. It agrees with Kolmogorov complexity. No, it's not. You can state precisely and then you can prove it. It's like,
It sounds very dubious.
What?
Vague, the conjecture is vague.
No. Okay, let's give an example. So example. For example, you take some transcendental number like e to the p square root of 2 something, yeah, and make conjecture is digital uniformly distributed. This unprovable. Yeah? And this is pure. You can take this kind of digitals using a pseudo-random generator for Ramsey graph and say these are Ramsey graphs. It's unprovable.
But you think that it is possible?
No, he thinks so, yeah. No, it's unprovable in arithmetic. It's unprovable in arithmetic.
Interpretation of this conjecture will be either false or unprovable or uninteresting.
No, because you have a majority of them. There is Kolmogorov complexity, stating that if you can compress random function or random loop compressed, then some results stay inside the framework. Most statements are unprovable.
But could you imagine a proof that it's possible to prove that pi is a normal number in binary?
Yeah, certainly, yeah. It may be quite a theorem. So it's unprovable. It's improbable arithmetic, yeah. Certainly. Yeah, of course.
It's a belief about the structure of mathematics that most such statements, it's not a conjecture. It's my belief that most statements of that sort, which are overwhelmingly likely on probabilistic grounds, but do not respect the structure of the problem, like the digits of pi to the Euler's constant or something, then let's say if it's unlikely, if you conjecture that half the digits of that number are 7s, that must have a proof. I mean, if it's true. It can't be true. But if it's a random statement, then I would think the vast majority of such statements cannot be proved. There's no reason that just because they're true, they're provable. They're simply true on probabilistic
The
grounds.
normal number is the best. That's the best example.
Yeah, exactly.
Yeah, I think in binary I can see why half the numbers cannot be 7.
This is not really a counterexample to this, but a little bit in the other direction, which says that, that say the roots of square root of 2 are not really random. If you give me say a k, and you say this number is the root of a polynomial where the sum of the coefficients, the logs of the coefficient is at most k or something, and then you give me then after a polynomial number in k of digits, looking at, if I look at a polynomial number of digits, I can compute the rest. So it's not a good. It doesn't really look truly random. After a relatively short part, the rest is computable.
But maybe it looks really random. Why would it's a computable random pi have anything to do with Ramsey graphs?
Oh no, it has nothing to do with random graphs. I'm just saying that that there is some regularity in the digits.
There's no regularity?
Well, it is. It says that
if you give enough digits, you can identify the number. Once you have the number, you can compute as many digits as you want.
Right.
But that doesn't mean there's any regularity in the digits. If I simply tell you my number is the square root of 17 plus the cube root of pi, you can compute the digits. That doesn't mean they're regular. You're just saying that a finite, an algebraic number.
But you don't tell me that it's square root of 7 plus square root of pi. Well, all you give me is some upper bound on the complexity, which.
Well, that's a finite list. So
no.
Some of.
Yes.
Yes, it's a finite list. So even.
But it's an exponentially large finite list.
Part of the conjecture is actually what Avi talked about. It's difficult. It seems related. It's not. So some things are difficult, and it's difficult to prove them. Something that it's difficult to prove some things behave randomly, and that if you find the proof that they behave randomly, then you'll get contradiction to other beliefs or other pseudo beliefs. So there is some theorems in the direction of some interpretation of this meta conjecture, but
Right.
but it's very.
Yeah, I think maybe we can sort of corner you down to exactly what your statement meant. You meant it's a sequence that is generated with.
I think he was talking about normal numbers. I think he was saying
No. This is an example. No,
It's a statement about mathematics, not about
yeah. So it's a statement about mathematics.
But it's not a conjecture to believe.
No. I understand, but we can try to specify exactly what it meant, and well, we don't have. Yeah, I mean, but at least following Latsi, there is one example of things that you guys know how to prove about sequences that behave like random. For example, the Veil theorem about character sum. So if you take, so the sequence of character values of a polynomial over a finite field do behave in some sense like random coin flips, right? So your point was that when we say that something is random, we really mean a particular property, and the property can be, let's say, how it behaves in intervals, or in the case of Ramsey numbers, is what happens to the largest clique. And you can. You said that if it's not related to the original problem, maybe it's hard to prove, even if it's true. But in those cases, it is
I'll
related.
ask him a telling example,
Yeah.
which I think will prove. Take those numbers tau of p.
Yeah.
There's a conjecture that tau of p is never zero. Do you think is that an example of an unprovable nonsense?
No idea.
But you said you have a feeling. You have a feeling.
The statement doesn't apply to any particular theorem. It says that the set of theorems which are provable has measure zero. If you ask me whether a particular theorem belongs to that, obviously depends on the future. If you find a proof.
Yeah, but
On the other hand, if you ask me
I
whether...
don't really know what the
Okay.
statement is.
No, you can organize also.
It wasn't meant for public discussion.
Yeah, okay, so you're talking about something
It's
complete.
not meant for public discussion. I mean,
Yeah, it's too late, Don. It's too late. So I think we have at least one controversial thing coming out of this discussion. So any more controversial statements? Or
No, it's
uncontroversial?
controversial. It's absolutely solid. This is what he says, a very feasible statement. Arguing against it is impossible. It's absolutely feasible. It's impossible to deny what he says is correct. If you don't accept it, you didn't follow what he said.
But let's take
Once I heard it, it's clear.
I'm addressing this.
You will dominate everyone. Yeah,
Let's think, yeah.
if you just talk to this, you will.
One second. So let's take this specific example of the normality of pi, let's say. So it will be very surprising if someone can prove that pi is normal, because people believe that that's very difficult. But to me, at least, it will be much, much more surprising if someone would prove that it's impossible to prove that pi is normal. I mean, that's okay. So that's only, but still, you believe that it's impossible to prove.
for any specific problem. For any specific problem, I'm not willing to make. Well, some might think that.
You can write some incredible number, massive number, and then can bet it's unprovable. It's random. Pi is maybe take pi to the early constant multiplied by some rationale, make this big thing, and then you can bet ahead.
If you would like to make a statement,
Do you believe that most theorems will not be proved?
yes, basically yes.
No. Naive theory.
Most naive theorem will not be proved.
Okay. There are more than 100 people here. Why does it matter what I believe?
Okay, Tim is holding the mic.
I just want to take issue with Misha's.
You point the camera here, please.
With Misha's suggestion that it's completely impossible to imagine this statement being disproved. Because one could I'm not saying this is likely, but one could sort of imagine in one's wildest fantasies some sort of big meta-theorem that says, unless there's a good reason for something to be non-random, then it's random, or something like that. So that anything that you write down that's stupid, like the digits of e to the root gamma or something, must behave randomly. But if you try to prove it within some more restricted...
Getting out of arithmetic,
Yeah, exactly.
will be random. However, it's unprovable arithmetic. That's exactly the problem with the situation. You can prove outside of arithmetic, most of them will be random. But in arithmetic, it will be unprovable, most of them. That's, I guess, the most likely situation.
I wasn't going for a counting thing saying most of them were random. I'm saying they were all random unless there was some identifiable property that sort of...
You cannot define the property. The property will be undefinable against arithmetic.
This is the mathematics.
Or maybe a positive measure set of them or something like that. Okay. It's just a wild fantasy anyway.
We're talking about different degrees of randomness here. I mean, of course, yeah, so of course the other end is that something is random if the Kolmogorov complexity is as large as its length, and of course this doesn't apply to any of these. And then there is a notion in cryptography where randomness would mean that yeah, looking at the first k digits, you cannot predict the next one in polynomial time with any non-trivial success probability. And then there are various other notions of randomness, like in graph theory, it's quite nice to look at, quite interesting to look at quasi-random graphs, which is a well-defined class of graphs, including Paley graphs and others, which have several properties of randomness. And I think in same for real numbers, it's like normality would be a notion of randomness.
I should just say my actual statement right now.
Oh, quasi-random means, well, one way to define it is that the degrees are
maybe the simplest is that every finite subgraph appears the right number of times.
right.
4 cycles is only enough.
Yeah, so there are several, I mean, there are 10 or 15 equivalent definitions in terms of spectra and so on. I mean, and that's the interesting part, that they are all equivalent. That means that it's a robust notion. And so so in this sense, I agree with you if you talk about normality or some similar version of randomness.
Since it's been quoted, had nothing to do, first of all, with normal, but also nothing to do with random. Because the statement about all mathematical statements, nothing to do with probability and randomness.
Then please.
Okay. So I have no idea how this happened. I certainly I shouldn't have had dinner with Misha.
But just note that you are being recorded.
Of course. So we know from Gödel that many true statements, in other words, statements which don't contradict the axioms of mathematics, cannot be proved. My statement is that, or my belief simply, is that we shouldn't be surprised if actual mathematical theorems that come up, what people call conjectures, often belong to this class, if they are of the sort that they say that the expected behavior is what happens. So for instance, take Fermat's last theorem, before it was proved. Certainly I would not have conjectured that it could never be proved because it had a lot of structure, and indeed it was proved. But in that case, my statement would have said, even if it cannot be proved, it is surely true, because on probabilistic grounds, if you compute the probability of finding a counterexample, you'll find it's less than 10 to the, I think, a billion at the state that we were numerically before Wiles. So in other words, I'm distinguishing statements, mathematical statements, which are overwhelmingly likely and overwhelmingly unlikely. If you make a conjecture which is overwhelmingly unlikely, and you're not an idiot, I mean, you have some reason for it, it must have a proof. So say the Birch-Spinet and Dyer conjecture. It says the two numbers are equal. It's been tested in thousands of cases. They're real numbers. You test it to 50 or 100 digits. It's extremely unlikely. Such a statement cannot be, in my philosophy, unprovable, because there must be a reason that it's always working, and that reason, when we find it, will be the proof. But when you make a statement like Fermat's last theorem, which on probabilistic grounds should be true because there's no earthly reason it shouldn't, then I believe that many of those statements cannot be proved, not because we're too dumb. There is no proof. There's no finite sequence of arguments. I don't mean anything metamathematical, just we shouldn't always expect that such things are theorems. They may just be random facts. And an example was things like the normality of numbers that have no... Of course, any given statement, like that zeta of 3 is irrational, maybe can be proved, and that one was. Zeta 5 still hasn't. I mean, I'm not saying that any given statement that numbers, let's say a given number behaves randomly, is necessarily unprovable. That many such statements may be unprovable. They are surely still true. But anything which looks correct but is very unlikely must be true and must be provable. So it's a sort of a way of distinguishing two kinds of statements. It's a much more philosophical, it's certainly not a conjecture, but a kind of religion.
Actually, I want to add one thing to that. Firstly, every time he talks, perhaps you could talk after him. Because now I know what you were saying. I had no idea what he was talking about. But even so, it was
several times. Yeah, it was completely.
So I agree completely that the best conjectures are ones which are sharp So if you take something like the ABC conjecture, I think I would already have problems with that, as opposed to Ramanujan's conjecture that tau of p is less than or equal to 2 times p to the 11 over 2. If the conjecture said tau of p is big O p to the 11 over 2 plus epsilon with unspecified constants, it sounds much less, it sounds like his second category. That might be true, but since it's not a sharp statement, it probably doesn't have a proof. And there are many conjectures, the Lindelof hypothesis. The only reason we believe that is because of a clean conjecture like the Riemann hypothesis, which you check millions of zeros down the line. Once you understand it, it's got to be there. So I think that
comment on that. He explained to me that
Riemann may be a hard one.
No, but he said it's not the wrong interpretation. You have to go further.
Okay, anyway, I think that the point he's making is a very good one, and it distinguishes something like the Birch-Winnet and Dyer conjecture from the ABC conjecture, where there are unspecified epsilons
Goldbach conjecture.
and constants.
No, but Fermat-
Goldbach is a...
No, Fermat's theorem is completely well defined. But it's,
Fermat is good. I never said
no,
Fermat.
it's in the opposite class from Birch. No, Fermat.
Absolutely, it's opposite, yeah. Fermat kind of conjecture is not expected to be true.
One and not zero.
Yes?
But if you transform the Riemann conjecture and say that the sum of the mu function is about n to the 1/2 plus
It would be
epsilon,
much less
then
believable.
it seems
Yeah.
to go from your first class to the second.
No, but he's...
No, it's right.
I
So
mean, the sum of
I
the
agree.
mu, I mean,
But
it
don't
behaves
have- no,
like
but-
random. It would be.
No, but
Yeah.
don't never explain his view on the Riemann conjecture. It's not so simple, yeah?
Sorry?
It's not so simple. Riemann conjecture, don't explain to me. It's implausible up to some point, then become plausible for some particular reason. It's not just like that simple.
Well, what?
No,
yeah.
this
Okay.
abstraction
Yeah.
there, you have
Some
to
of my
understand
colleagues,
before-
two of my colleagues, Katz and Sarah, have suggested that we remove the big O notation, because any statement A is big OB without an implied constant is not a statement that's meaningful. And if you put a random constant there, then it's already, you're not making canonical sense. So they've gone to the point where if you're lecturing and you put big O, the guy will have, as you know, get very excited.
So just a second, Sasha wanted to say something. So I think just because some people are leaving, I suggest that we end it in about 5 minutes and continue it around the lunch table.
Actually, I just wanted to comment on the situation because many people they said something like this can be proven or this cannot be proven, and it seems people start to take it seriously. So let me just comment on the situation. Well, I am a mathematician, even if it doesn't show right from the first side. So, and I think one really has to specify which logical system are you talking about. Are you talking about set theory or Peano arithmetic or something else? If you want our discussion to be serious, then you cannot just say Peano arithmetic. Then the situation here is really miserable because there are only a few natural statements which are not proven and they are of totally different character. So if you really want to show something along these lines, this is a major open problem in the mathematical logics, and any example would be okay, but we really don't have even any approaches to that currently. But it's, well, I maintain that it is not something which is inherent for randomness or for Fermat-Lass theorem or whatever we like. It's simply the logical problem that we really don't know even how to approach these things. Thanks.
Some more comments. Yeah, if you come here, you will also be seen.
Actually, I'm not sure I want to be seen because I'm risking revealing my total ignorance of logic. But I thought there was a theorem that said that if something's undecidable, then there must be a model in which it's true and a model in which it's false. So if you take something like, say, the Goldbach conjecture, which is also thought to be true on probabilistic grounds, if it's undecidable, there would have to be a model in which it's false. If there's a model in which it's false, there would be 2 primes, an even number which you could check. Was not the sum of 2 primes, and then that sort of transfers to any other model. So, is that wrong?
The other side, it's true.
Okay, so I have revealed my ignorance of logic there.
Otherwise, you're right. It's true. It's undecided. It's both true and false, which is a little much to believe.
No,
Yeah. I mean, if it's false, there's a counterexample, and that counterexample can be written down.
Same with Riemann.
okay.
You can only identify false.
Somebody else better say something. I don't want that to be the last word.
Nothing.
Yeah, I just want to make one sociological.
Wait a minute. You have to talk loudly to the microphone.
Okay, I just want to make one sociological comment. Perhaps we've seen this recurring difference in attitude towards what a conjecture is and how lighthearted you can be when you make a conjecture and so on. It seems to me the one big difference between us and you, combinatorialists and so on, is that it's usually much easier to, or at least you can view it as a much more accessible goal to find a counterexample. If you make a false conjecture about graphs, at least you can imagine that either you draw some examples on paper, or perhaps you send a student out and tell and ask this thing to be checked on a computer, and perhaps the student comes back and says, I found a counterexample for a graph with 72 vertices. And so therefore, false conjectures in combinatorics perhaps have better chances to be caught just by checking. And therefore, perhaps you are not so scared of the O notation. Also with the O notations, you can ask the student, okay, draw the graphs of these things to me, and then you will see, okay, this cannot be, you can already see that this is not logarithmic behavior, and then you shut your big mouth and you don't tell anyone your conjecture, and the student won't tell. And this could be the reason why the attitude is different.
About the O notation, I just remember a story about a guy in MIT that at some point decided to replace the role of epsilon and delta and little n and big N. And then he completely got credit. So I don't suggest this. I just wanted to end with some concrete problem which attracted a lot of attention in combinatorics and an area which is not presented here. And still, it has now been proved, but it certainly belongs to the class of problems that Don would expect a proof. And this is the following problem. You start with the number 1, 2, 3, up to n, but I will end at 3. And then you write some triangle like this. Between 1 and 2, you write a number which is weakly between 1 and 2. In this case, let's say 1. Between 2 and 3, you write something which is between 2 and 3, let's say 3. And then here you write something which is between 1 and 3, let's say 2. So, and you ask how many triangles like this are there. So this is a function of n. And there was a conjecture that this is 1 factorial times 4 factorial times 7 factorial up to 3n. We'll see 3n minus 2 factorials divided by n factorials, n plus 1 factorials, up to 2n minus 1 factorials. Now we will check. This is the, so for example, for n equals 3, we have 1 factorials times 4 factorials, 3 times 3 times 7 factorials divided by 3 factorials times 4 factorials times 5 factorials, which turns out to be 7. And this is the right number. And this certainly belongs to the class of problems that you would say after you discover this relation, there must be a simple proof. Yet it took a... What? Oh, no, I don't. I took I think we should go away from discussing your meta conjecture. So I just want to say that now there are 2 proofs of this theorem, and the first proof was done using a lot of computer work also by Don Seilberger, and then Greg Kuperberg found another proof based on some work in statistical mechanics by several people. But still, this seemingly extremely simple formula does not have very simple explanations. So I mention it.
So I think that, we reconvene when you solve this problem, and